Hi everyone, my name is Joan Espasa and this is joint work with Özgür, Akgün, Nguyen, Miguel, András, Salamon and Christopher Stone. Why we're focusing here on instance generation? Because we think that having a varied set of benchmarks is crucial to be able to evaluate solvers and to learn their strengths and weaknesses. Also because when a community uses the same benchmarks over and over, it can become a problem called overfitting, and we do not want that at all. This work we built upon a work presented in CP in 2019 and 20 that uses the SNCP toolchain and iRace to be able to, given a problem specification in essence, use Conjure to generate or to translate that to the problem of generating an instance for that problem, and together with iRace is able to guide the search to extract valid instances with properties that we want. And our aim here, more concretely, is to extend this system to support automated instant generation for planning problems. But first of all, what is planning? We focus on classical planning, and a classical planning problem is or can be defined as a set of propositions or Boolean variables that define our state, a set of actions that are formalized as pairs of preconditions and effects that they mean what has to happen in the state to be able to execute that action and how that action changes the state. Then an initial state that says how our system starts, and the goal that is nothing more than a formula over the set of variables that define the state that any goal state must satisfy. PDDL is the de facto modeling language used by the planning community to define planning problems. And how does it looks? PDDL problem is nothing more than something resembling this, where you define a set of types and a set of predicates. Well, as you can see, each predicate has a name and a set of parameters, and these parameters will be instantiated with all the objects of those types to be able to generate the ground set of variables that will define our state. Actions also have a set of parameters, will be instantiated in the same way as the predicates, and also have a precondition and effect. This is an instance that we give the instance a name, we link it to a problem, and here we define the set of objects and the types that will be on our concrete problem, and our goal or the formula that will say when we have reached or we have finished executing the problem, and the initial state here that defines where each robot starts, what color it has in each hand, etc. etc. These 8 predicates here define something like this. That is a 4-tile grid by using these 4 predicates up, down, right, and left. We will come to this a little bit later. In our previous work, we use validity constraints or where constraints to be able to restrict the input space. This is available in Essence, and it has proven very useful to guide the search for the graded instances. The problem that we have here is that PDL cannot express them, and they can be necessary when you have complex assumptions on your input. Imagine that you have the up, down, left, and right predicates as before, and you try to randomly generate instances that resemble a grid like this. It's not complex to imagine that stumbling upon a valid instance there, it would be very difficult, almost impossible. So Our approach here is to say, okay, we just have to augment or extend PDDL to support this kind of constraints on the input. Our objective will be then to have a PDDL file with the description of the problem and using Essence to express these validity constraints. Our first approach here was to add just a new set of keywords into PDDL with keywords like at least, at most, mean, max, etc., to be able to express these validity constraints, and to add on the front of the system a translator from this PDDL to Essence, and on the back of the system a translator from Essence to PDDL. We are able to do that because we know how we translate from PDDL to Essence, so we are able to automatically translate from Essence to PDDL back. The good thing about this approach is that the user only has to give us one single input, right? But the problem that we have found when implementing this is that there is a very limited flexibility in specifying the validity constraints due to the low-level representation of PDDL, as we basically only are able to use sets of booleans. And this led us to quite bad scalability problems that you can see in the paper. So we came for a second approach, and we said, okay, maybe what we have to do is to express the validity constraints in a separate file, and as we know how these PDDL variables are translated to Essence, we can just use this knowledge to express constraints on those, and afterwards provide an instance converter from the result to PDDL back. The good thing about this approach is that you gain in flexibility, because now we can use the full power of Essence using things, for example, sets or functions, and we have much better scalability. But the bad thing is that there is a serious lack of automation here, as the user has to give the system 3 different and connected inputs to be able to solve this. So our thought went to the fact that as we are transitioning from PDDL to Essence, what about using Essence for the whole thing? That would simplify our approach quite a bit. And this was our third approach, that is expressing planning problems completely in Essence. What we would gain from here is in flexibility and scalability, as we would be able to use the high-level data types not only into the expression of the validity constraints, but in all the problem, leading to states that are structured like this instead of big sets of booleans that resemble something like a SAT instance. As you can see here, our state would have two different, well, it would be a record with 2 different fields, the robots, that would be just a sequence of the number of robots, and for each one it's a record that we could say in which row and column the robot is and which color is handling, and finally how our grid changes with time. So this would be only a single input by the users, and as our toolchain already supports translation to CP, SAT, SMT, and various formalisms, we will need to extend it to translate these new planning constructs, and we could add refinement to PDDL. So the takeaway from this work is that PDDL has very limited expressivity and is not quite well suited for automatic instance generation for planning. We believe that expressing a planning problem using a high-level modeling language, such as Essence, will solve our problems, and not only that, but also will help in modeling new ones. And our next step would be to implement this described extension in Essence. It would be a lot of work for the implementation, so we want to know if the community would like it, so please let us know what you think. Thank you.